Greetings, this is Artie from Artifact Electronics. So we saw the unboxing last time and things started to move into the basement. I pretty much have moved everything into the basement. I have started setting up machines, starting to get them to work and all of that, but things aren't going as fast as I'd like them to go. Atari boards or Atari machines don't have a very good reputation. To start off with, they were more expensive than the competition. They were different. They were all wide bodies. They worked not completely differently, but significantly differently than the other machines out there. So it was kind of a steep learning curve to get into them. And also they didn't make that many of them because they made machines from the mid-70s to the early 80s. I think a total of 7 or 8 machines. And then they stopped making them, and I think one of the reasons for that was that they weren't overly popular, they weren't hitting sales goals. And also around that time, late 70s, Warner Communications bought Atari, and I guess they looked at the numbers and they said, hey, why don't you stick with what you know best, and that's video games? So they shut down the pinball division. Quite a shame, but anyway, in this episode we'll have a look, we'll get an overview of how the electronics work in the Ataris, see if the difficulty of fixing them is a myth or a truth, and that'll give us a much better understanding once we look at actually working machines, which I'm planning on getting working really soon, especially since all 6 machines use identical electronics. So when you fix something on one machine, it usually applies to all of the other machines too. And the background or the theory of operations we're going to talk about in this episode about the electronics applies to all of the machines in equal amounts. So let's dive in. In my opinion, one of the major problems with the boards was, I think, of a mechanical nature, and that's these sockets. I mean, you ever seen ridiculous looking sockets like this before? I don't know, maybe they got a good deal on them, but they, even though they look nice, here's one I've removed from another board. They look nice and they seem to have the gold-plated contacts, but they're not very reliable. What you're looking at here is they have the processor socketed, of course, which is a 6800. I don't know if you can see that. Let me see if I can zoom in on it, but it's kind of cool. It's a 6800 with the Atari logo on it. So I guess they bought enough of them to warrant Motorola labeling them specifically for Atari. What you see in the back is, here are 8 bipolar PROMs that hold the operating code. And there's also 2 24-pin sockets because eventually they switched over to the bigger PROMs over here, which did use less power. But note, they're all using the sockets the size of a small building or garage. And I mean, with cheaper sockets, you look at them, you can kind of see that the pins are corroded and things aren't going right. But on these, because they're gold-plated, they seem to look okay, they seem to clean up okay, but these cause a lot of problems. So probably one of the first things to do with these boards would be to remove these sockets and just put more modern sockets in them, preferably the ones with machine pins. And again, this is really difficult to remove because of the way this is soldered to the board. I mean, you can't cut the pins off. You can't cut the body of the socket because you'll destroy the board with the stress you put on all the pins. You just have to be really, really patient to get these things out. I fixed quite a few problems on these by replacing sockets. And sometimes you can identify the problem really easily by turning on the board and then pressing onto chips. And when you see that that fixes the problem or makes the board boot, well, guess what? You found the problem. Other problems I found was, remember, I got a whole bunch of extra boards, and I plugged them all in, and none of the 21 boards that I got with my purchase worked. But when I paid more attention to it, I noticed that they used to have, I'll show you a board later, but the old style, the really big crystals that stuck above everything else. And about half the boards I got had the crystal broken off. I mean, I couldn't see the forest for the trees, but the crystals were just missing because they were all stacked together and I guess got sheared off. And some of the boards actually came up after putting in a new 4 megahertz crystal. Other issues are the 5-volt regulation, which happens on the board itself. It is fed basically unregulated 5 volts, which is like 11 or 12 volts. Has an LM323K, which is a 3 amp, 5 volt, 3-terminal regulator, some small ports, and then we get to this resistor over here. It's a 4 ohm, 10 watt resistor that is connected to the input, that basically shunts the input to the output of the regulator. And it took me a while to figure out why this was here. I mean, I've seen a lot of ways to modify a 3-terminal fixed regulator, including things like putting a pot on the ground connection so you can actually adjust the output voltage, putting in large resistors in series with the input, and what that's for is to reduce inrush current when you're first turning it on. But see on this board, I mean, they got a whole bunch of bypass caps, but this cap is the biggest cap on the board, and that's sitting across the 5-volt rail. So inrush, I guess, wasn't a big problem over here. And let's see, what else? Protection diodes going from the output to the input, all sorts of things. But I could not find any reference to shunting the input to the output of the regulator with a big-ass resistor. And this thing gets hot, really, really, really hot. So let's have a look at the schematics to clarify this, and then I'll tell you what I figured out. So here's what the schematic shows us. This is the 5-volt regulation part, and here's the regulator, which is in a TO3 package. You saw that in the heatsink, and here is the resistor we were talking about. And again, to me, I had never seen this configuration, and this resistor turned really hot. So what I did was I took a board and I removed the resistor, and the board worked just fine. Then I took a second board and removed the resistor, and the board didn't work right. I mean, it started to reset after about 20 seconds, continuously. So that in itself should have been, or was, a big hint. And what it turned out to be was interesting. It turns out that this resistor is there to supplement the current sourcing capability of the regulator. So we know the regulator is basically rated at 3 amps. So if heat sunk correctly, it should be able to deliver 3 amps. Problem here is that the heatsink is, I mean, I haven't done all the calculations, but it looks a little small to me if this thing were to deliver 3 amps. And also they're using heat pads here rather than using heat transfer paste on it, which reduces its current delivery capabilities somewhat. So what I found was that the board that was working correctly with this resistor removed was drawing about 2.7 amps. So it was kind of getting borderline, but this thing was still able to deliver the current to maintain that voltage. But the board that failed when I removed this resistor, when working, was actually drawing 3.4 amps. So it was clearly drawing too much for this to deliver. But when I put the resistor back in again, it worked. Aha! So that's a way to cheat and get that regulator to deliver more current. And after pulling my 1982 National Semiconductor Data Book and actually looking up the LM323K, it turns out that in one of the suggested circuits, that's exactly what it does. You're creating another path for current to pass here, and that increases the current delivery capacity of this 5-volt supply to be able to handle the boards that were drawing more than 3 amps. How does that work? Well, it turns out that one of the footnotes on this regulator says that you can do this, and as long as the current going through this resistor is less than the current going or coming out of the regulator, that's fine. It is a permissible thing to do, and the regulator is still able to regulate the output, again, as long as the current going through here is less than the current coming out of here. So that was, I guess that was the official explanation. Now, why did one board work, and why were some boards drawing more current than others? And I think I figured that one out too. So here's a board that did not work when I took this resistor out. And when I compared it to another board, even though it's got a full complement of sockets over here, this one uses 8 bipolar proms. And these little guys, don't be fooled by their size, they're pretty power hungry. So this board actually consumes approximately 3.4 amps. And that obviously overloaded this. It kept going into thermal shutdown in a rapid fashion. And the board kept resetting. So when you had a board, and let me see if I have one handy here. Oh, here's a board. But basically what I did on this board was I pulled the bipolar proms, and I burned 2732s. It took very slight rewiring to make that work. And as you can see, the resistor is gone over here, and this board works fine. Doesn't reset. Well, it works fine when you put a processor in it, but it doesn't reset, and so that kind of proves the whole thing that the regulator needs the cheat resistor to be able to supply enough current to a board that uses more than 3 amps. But you knew that already. Well, I didn't, so it was interesting to finally figure out why it did that. Another thing is you can see a bunch of blue wires on the board. They went through several revisions on the board. These are definitely not field upgrades but factory upgrades, because the wires are run very neatly and under chips and all that good stuff. So let's see, another issue I found. Here's a reset switch, and I found 2 or 3 boards where the reset switch, I guess, had gotten dirty or whatever and was stuck down. So basically the reset signal never released, and thus the board couldn't work. Those, in my mind, are the major problems with this board, and if you know about them, yeah, it's kind of a pain in the neck to have to replace all of the sockets, and it's not always necessary. I mean, I still work on the principle that if it ain't broke, don't fix it. And I have several boards running with these large sockets in them. But when things start acting up, or the board won't boot up or whatever, that's when I start replacing sockets. I mean, first I move sockets around, press on the chips and stuff like that, and if that changes the behavior of the board in any way, well, guess what? It gets new sockets. Now, of course, other things will go wrong too. This board is made up entirely of early generation TTL, no LS here. It's all plain 74 some number TTL, and some of those go bad. And one of the reasons why that may get a little bit hard to diagnose is that, like all Atari arcades, first of all, this has a watchdog on it. So if the processor blows its mind, it resets the whole thing. So you don't, on a video game, you don't burn a hole in the screen. On a pinball machine, you don't burn the machine because you got a bunch of solenoids who are pulled in permanently. Even though the solenoids are fused, and later on I'll show you how this board looks in the machine and where all the fuses are and stuff like that. But you know, the idea is, hey, the processor just glitched, and let's just restart it. So when you're troubleshooting something and you keep seeing the reset signal on pin 40 here oscillating, okay, something's happening. Now, how does a watchdog work? It's got a counter chain here, and if the counter chain is allowed to run its course, it will essentially cause a reset. But the way this works is the processor periodically, every few milliseconds, resets the counter chain if things are working correctly, so a reset is never generated. Obviously, if the counter chain is allowed to runs its course and resets, that means the processor never got a chance to reset the counter chain, and something bad's happening. Bad ROMs, bad logic, bad whatever. Now, you can disable that, but that doesn't make a whole lot of sense, because if the watchdog isn't working, you already know that there's something wrong in the logic. So even though the manual tells you, you know, disable the watchdog circuitry and fix whatever's wrong, I don't know. I haven't found that to be very useful, but I guess for some people, either disabling or leaving the watchdog on still, they still figured it was really difficult to repair these boards. Now, where it gets complicated is Atari used a unique approach to minimize the number of latches and do some hardware reduction on this by utilizing DMA. Direct memory access means that the processor goes to sleep, and then there's logic that picks things out of a certain location of memory in the address space and puts them somewhere else, all on its own. And as you can see, there doesn't seem to be any LSI chips that would be the DMA controllers, and that's because it's built out of discrete logic on this thing. And the reason they use DMA is so the scores, the state of the light bulbs and stuff like that are all written into RAM, which are 2111s, which I think are 128 by 4 RAM chips. So under the normal course, I mean, if you were to write to the light bulbs directly, you'd have to latch them somewhere, and you need a lot of latches. Because even though the lights are multiplexed on this, it's only got 4 columns of lights, so you'd still need a lot of latches to do that. So what Atari did was, you write all the values for displays, score displays, lamps, and so on into RAM, and then every so often the DMA circuitry kicks in, disables does a bus request on the processor, and transfers the all of the display bits to the output drivers. These are the lamp drivers here, and over here are the display drivers. And so they're saving, basically they're using RAM as the latches and having the DMA circuit transfer them periodically, and it works just fine. Now the problem with that is it does make troubleshooting a bit of a pain, because even if you, let's say you pull the processor out of this thing and you tie the bus available line active I'm not sure now if it's low or high, the DMA will run. So you will see activity on this connector, which is actually DMAing stuff out of the display, or these two connectors, actually all three of these, that DMA stuff to the lights, but it's all garbage because it's DMAing stuff out of uninitialized RAM and the processor isn't even there. So when you're troubleshooting stuff, it is not straightforward because the DMA keeps coming in and making it seem as if there is proper activity everywhere, where in fact there isn't. You can also disable the DMA, but you see where I'm going. I mean, there's so many things you have to disable to just do a basic troubleshooting thing on these that I think that earned it the name of being really difficult to fix. It's not really difficult to fix, but and that probably had something to do with Atari leaving the pinball market, which really was a shame. Other than that, we have the auxiliary power board, which pretty much does everything that nobody else does. It's got the audio, it's got half of the audio generating and then the audio amplification circuitry on it. It generates the anode and cathode voltages for the gas discharge displays that show the scores, plus minus 90 volts. And as I mentioned before, it basically has 4 columns of all of the light bulbs on the playfields or on the machine are divided into 4 columns. And here are the 4. This thing supplies power, 20 volts to the positive side of the lamp chain, and these basically ground a column at a time, letting you scan 4 columns. So what that really means is the bulbs, 20 volts is a bit high. Those are actually number 47 bulbs, which are rated at like 6 volts or so. But because of the nature of this, even if you have a light bulb, if the light bulb bit is on permanently, because it's getting scanned, you divide that by a factor of 4. So the duty cycle is 25%, even if something is on. And, you know, that would take the 20 volts down to about 5 volts. And that's pretty much what this board does. And those are the 2 major boards inside the machine. Finally, we have the score display and ball credit display over here, gas discharge displays that can show 4 6-digit scores, tells you which player is on, and then these are just 2 digits, 7 segments that show you sorted information. Because they're gas discharge displays, they need plus minus 90 volts to operate. For some reason on these, the plus 90 volts is usually good. It's the minus 90 that goes bad. Of course, if it goes bad, the display is blank and nothing happens. And that seemed to happen quite frequently. So that probably had something to do with the operators not liking the machines too much. But that pretty much sums up what's in there. Probably be useful to have a look inside a machine to see where these boards are mounted. And then I think that gives you a really good overview of how these machines, or what makes them tick. So here's what the inside of a machine looks like. The one I'm showing you is probably the one in worst shape. It has had the most parts robbed from it. It didn't have a playfield glass and sat in the dirt for 10-15 years at a minimum. But here's another problem spot here. See how the board sits right underneath the playfield. And it is not uncommon for things to get loose on the playfield and fall straight down and short things on the board. That was another problem with these machines. They did have a protective plastic plate. See those brackets on either side? They're missing in front. My lamp is falling down. stay. Great. There you go. But most operators, whenever you have to change settings on the game, you see there's 2 banks of dip switches and a rotary, a hex-encoded switch with which you set the game options, difficulty, replay levels, and stuff like that. So people would take those out and not put them back. And then things would fall on the motherboard and short the motherboard. There's the auxiliary power supply. That big ugly ribbon cable goes to the display, which sits on the left side of the apron. Here, of course, is the playfield. This one is missing several parts, both on top and bottom. And the one part we didn't see before is the transformer assembly. You got to give it to Atari. They did not skimp on their transformers, either in video games or pinball machines. That transformer is about 4 times as big as it is in a Bally pinball or Williams pinball of the same era. There was a video on the Bally Playboy I did a few episodes back if you want to see that, but that is not a source of failure. It's got that. It's got like 25 or 35 amp bridges sitting there, and in all 6 machines I've looked at, there's nothing wrong with that part. The transformer works fine, the bridges are all good, and the wiring's good, and even, you know, the big caps are good too. I mean, big caps like this don't go bad that often, and that should not be something that you immediately replace, unless, of course, things are going wrong. Now, one thing I've achieved is I have 6 working board sets. So the machines boot up, and to prove that to you, it's running the lights. So pretty much the boards in here work. Some of the solenoids don't work, but I still don't know if it's the solenoids or the driving circuitry on the board. And the last thing is that I didn't have on the bench was, see that board plugged into the motherboard? That basically contains a fuse, an individual fuse for each solenoid. So unlike other machines which just had one fuse for solenoids, and this actually has a fuse per solenoid, which is a really good idea, because you can immediately, I mean, if a fuse blows, you'll immediately know what blew it. And that's about it for this episode. What I'm trying to do is get a machine up and running so we can see what it looks like in all its glory and actually play a game on it. It won't be as long as it was to put this episode up. I'm making good progress, but pinball machines are very mechanical in nature and need a lot of adjustments. I mean, when the electronics work, they work, no problem. But adjusting the flippers, adjusting solenoids, and just making sure that everything's fine, the playfield's clean, the ball isn't getting stuck and stuff like that, it does take a while. But I promise I'll do my best to show you an actual working game, or maybe 2, and we'll play a game on it and you'll see what it looks like with the hood down. Thanks for watching. Make sure to subscribe if you haven't already, because you definitely want to see what these beauties look like when they're working. Thumbs up would be appreciated. These things, I mean, so far they've taken a lot of work, and they're going to be taking a lot more work. So it would be great if you showed your appreciation that way. But we will see you real soon. I promise. Happy pinballing.